Hello, everybody. My name is Osbel Almora, and I'm very happy to present you the Emerging PV Reports Initiative and article. So in the next presentation, I'm going to talk first about our motivations and the main idea behind the Emerging PV Reports and database. And later, we will be discussing about the representations and the main content that you will find in our first publication. At the end, we will provide our conclusions. So the initial concept of the main PV reports arises because of the need of our community for a reference guide for the best achievement in the research in photovoltaics. So currently, what we mostly use are the NREL's chart for best efficiency in photovoltaics as a function of time. So you can typically see here the absolute records for each efficiency as a function of time. And this is very cool. Everybody want to show. And if you manage to get into this chart, you are very proud of your results, okay? And you can also use the solar cell efficiency table for Martin Green and co-workers, in which they provide a little bit more information like the performance parameters and a little bit more details about some other areas inside the photovoltaics, like concentrated cells, multi-junction. However, these references are not really targeting some special applications like transparent and semi-transparent photovoltaics, flexible, high band gap photovoltaics. And we have here only the references for certified performances and not so much about the published peer-reviewed articles. In addition, we have no idea here about what is the stability of the devices once they are certified in terms of efficiency. So basically, this reference right now allow us to say, okay, we have the Usain Bolt, the fastest runners on Earth in terms of photovoltaic efficiency. However, if we want to highlight a good result, an outstanding performance in a research solar cell, we need to manage ourselves to look in the literature and find all of these systematic reports on good devices which are already in peer-reviewed journals. So the alternative, which is the emerging PV reports, what proposes, okay, let's enhance our reach, and let's first provide a website in which you can submit your already published results, and we will be able to store and provide you with access and extra features for the data representation. You can go to our website, emergingpv.org, and also in a more immediate way, we can promote your results in our Twitter account or any other social media. And more importantly, we target not only the best solar cells, the best reports published in journals for absolute records in each technology, but we also target absolute records which are not certified, flexible photovoltaics, transparent, photostability, the time evolution, and in all cases, we put everything in perspective with respect with the shock whistle limit for the one junction PV behavior. In this case, we have already published the first version of device performance of emerging photovoltaic materials in advanced NE materials. And we are very proud to be working with a large number of colleagues representing several regions and several sections of the research in photovoltaics. What we propose here is basically to summarize in a periodic way every 6 months or every year for each different application, the best performing device as a function of band gap. And for that, we have some inclusion criteria. So in order to be highlighted as the first, as the most outstanding device in each category, we first require that each published report in peer-reviewed articles should present the JV curve, so we can evaluate whether the calculation of the power conversion efficiency was actually properly performed. We also require that the external quantum efficiency spectrum of each device should be presented and properly described in the device. So from the EQE, we can extract the bandgap energy from the inflection point of the absorption threshold, and also we can integrate the photocurrent, which is going to be used to compare whether this result from the EQE is really compatible with the photocurrent or short circuit current that you get from the JV curve. As a third element that we ask the authors to include in the papers or in the paper to be considered for the emerging PV reports, we ask the people to provide a proper description of the device or the complete design that we are going to be reporting, so we guarantee the reproduction of these results. In terms of each individual application, we also ask the researchers to, for instance, in the case of flexible photovoltaics, provide evidence on minimum bending radius, or for transparent or semi-transparent photovoltaics, the transmittance spectrum in order to calculate the average visible transmittance. And in the case of the stability test, we ask the people to provide in situ power conversion efficiency as a function of time, which will provide allow us to calculate the external energy that we can extract during the stability test. Or alternatively, you can also provide just the power conversion efficiency before and after 200 hours or 1,000 hours under elimination. So with this in mind, we reviewed on literature, and we found a lot of reports. And this is basically what you can find in the emerging PV reports. The most general representation is just the absolute efficiency for each bandgap. And in this plot, you can find, for instance, different technologies. We are mostly focused on emerging photovoltaics. And in each case, we plot as a function of bandgap, and you can see what is the distance between the corresponding efficiency and the limit in the shock liquidity. You can see that, for instance, most of the emerging photovoltaics, let's say organics and dye sensitized, are below the 55% of the shock liquidity limit, while most efficient perovskite solar cells are already close to the 85% of shock liquidity limit. Only gallium arsenide, everybody knows the record material, is that close to 90% of shock liquidity limit. This representation allows us to actually provide a plot for the losses in logarithmic scale representation for each one of the parameters included in the calculation of the power conversion efficiency. For instance, we can see here in this representation how for some devices the losses due to photovoltaic are more important, like in this case, than those losses because of photocurrent. And similar analysis you can see here. For instance, this is the open circuit voltage as a function of bandgap with the shock liquidity limit here, and the same similarly for the short circuit current, the photocurrent. So if we continue, we can find something similar for the flexible photovoltaics. This is the typical representation. It's very similar to what we just saw before. In this case, what we just found is that which is very obvious, that most of the reports are in the bandgap regions where the most successful devices have been reported. So for instance, for perovskite, of course, around 1.6 electron volts of bandgap is where we find the most efficient flexible photovoltaics. In the case of semi-transparent and transparent photovoltaics, now we have several ways of representing the best achievements for these applications. In this case, one of the most common ways is to just represent the power conversion efficiency as a function of the average visible transmittance that you can calculate taking into account the transmittance spectrum. You can also plot this instead of 2D. You can plot it as a function of bandgap also, which will introduce a third dimension, a 3D plot. And this surface here, this 3D surface, will be the non-wave selective shock acquisitive limit in 3 dimensions. You can also represent a very useful figure of merit, which is the light utilization efficiency, which is the product of the average visible transmittance times the power conversion efficiency. And here you can compare as a function of bandgap or again as a function of ABT. In all cases, you can find that, for instance, in the case of emerging photovoltaics like perovskites, organics, and some dye-sensitized, the results in transparent and semi-transparent photovoltaics are more relevant or more important, more significant than with more established technologies like thin film inorganic solar cells or amorphous silicon. This is very interesting. So we also find that the long-term stability is one of the most important in terms of what we need to focus in the future for the success of emerging photovoltaics. At this point, we don't have too many points in our graphs because there are not too many studies on, or there are not as many studies on long-term photostability as in other types of research areas in photovoltaics. And also, it is very common that people report long-term photostability without reporting the initial values. So you just plot some normalized graphs, and some authors forget to put the initial conditions or the actual, the properly described conditions of the stability test. So we cannot provide a proper comparison between the different points here. And what we show here is the stability test energy yield, which is basically the integral of the output power as a function of the time of the stability test that you can find after 200 hours or after 1000 hours. You can also find the power conversion efficiency after 200 or 1000 hours as a function of the initial efficiency. And also the degradation rate, the overall degradation rate, which is basically the difference in this degradation, in this power conversion efficiency because of degradation over the time of the stability test. With this, we arrive to the last set of plots that we provide in the emerging PV reports first version in Advanced Energy Materials, which is the time evolution of these reports. If you check here, you will find that there are some research areas or research sections in the research of photovoltaics, which are more recent. Like here, you see that we find a lot of research here in organics and perovskites. However, there are some sections in bandgap, for instance, which are which maybe in the last few years are not so attractive as they were like 10 years ago. And the same you can find for the semi-transparent photovoltaics or for the stability reports. With this, we get to our concluding remarks. So basically, don't forget to read our paper, our first emerging PV reports, which summarize on all of these best achievements in the research of photovoltaics. Don't forget to go to our webpage, emergingpv.org, where you can collaborate, you can access the data in a very nice way, and you can also collaborate, you can contribute with us and be part of our initiative. I mean, the main idea here is that don't waste time in looking at the literature in order to create these graphs in which you say, okay, my new report is a top report in this section. You can find this graph here, and if you don't find it, call us and we will find a way to include all new ways of representing the top performance in photovoltaics in our emerging PV reports. We also know that right now we still have a lot of work ahead. We need to include tandem, quantum dot, and some other newer technologies, which will be included in next versions of the emerging PV reports. At the end, I want to thank the emerging PV consortium and all the very nice people who have been contributing to our initiative, especially to the editors of Advanced Energy Material, Timur Gravel and Anna Troger, editor-in-chief and deputy editor, and the initiating members of the emerging PV reports. Don't forget to read our paper and visit our webpage. Thank you very much.